Good morning, dear students. Welcome to today's session of Operations Research. Today we are going to learn what is duality in LPP. We have already discussed what is linear programming problem, how to solve it graphically, and how to solve it using simplex method. So today let us go to duality in LPP. Here is a question for you. Write the dual of the following problem. Maximize z is equal to 3x1 plus x2 plus 2x3 subject to constraints x1 plus x2 plus x3 less than or equal to 5, 2x1 plus x3 less than or equal to 10, x2 plus 3x3 less than or equal to 15, x1, x2 greater than or equal to 0. So this is the question you are having. So first step, if you are having maximize in the problem, okay, objective function, if it is maximize, change it as minimize in dual, and if minimize, change it as maximize. That's the first step. Okay. Second step is just note down the right hand side of the constraints. Here it is 5, 10 and 15, and make these constants as the coefficients of the objective function. That's the second step. And next is just take the transpose of the matrix. Okay, here it is, that is of the subject to constraints. You are having the constraints over here, and take the transpose of it. I'll show you. Here for the first constraint, coefficient of x1 is 1, x2 is 1, and x3 is also 1. Okay, I'm writing the matrix from it, 1, 1, 1. And for the second, it is 2, no x2, so 0, and x3 is 1. Right? So 2, x2 is not there, so 0, and x3 is 1. Okay, and for the third constraint, x1 is 0, no x1, and x2 is 1, x3 is 3, right? So 0, 1 and 3. So this is the matrix form of the coefficients of the constraints. Now this is to be converted, that is a transpose of the matrix you have to take. So transpose means row will become column. So 1, 2 and 0, right? So you have to write 1, 2, 0 and then 1, 0, 1. So 1, 0, 1, and here it is 1, 1, 3. Okay, so 1, 1, 3. Okay, so this is the new matrix, the transpose of this matrix. Okay, now just write these values as a coefficients, and we know x variables we have to change as y variables. Okay, now come to the solution. I will explain again. Dual, here it is maximize, so go with minimize. Z dash is equal to the coefficients on the constants on the right hand side are 5, 10 and 15. So 5y1 plus 10y2 plus 15y3. Okay, now come to the constraints. Take these values. Y1 is here, Y2 is here, no Y3, right? So Y1 plus 2Y2, this gives the coefficients. 2Y2 greater than or equal to 3. What is this 3? The coefficient of the objective function. And one point you have to note is that this inequalities are to be reversed. Here it is less than or equal to, so it should become greater than or equal to. Say this, greater than or equal to 3. 3 is the constant coefficient of x1 in the question. And then come to the second one, this 1, 0, 1, right? So y1 it is 1, no y2, and y3 it is again 1. And The constant you have to take from the coefficient, second coefficient, it is 1. Okay, so y1 plus y3 greater than or equal to 1, here less than, and it is to be reversed. And the third one is 1, 1 and 3. So y1 plus y2 plus y1 plus y2 plus 3y3. Okay, greater than or equal to 2, the coefficient of x3. That's all. And then here x1, x2, x3 has been changed as y1, y2, y3 greater than or equal to 0. So this is the dual conversion. Okay, so this is how we can convert the given LPP into its dual form. And one more thing, prove the statement dual of a dual is primal itself. Primal is the original. That's a question. Okay, dual of a dual. That is first primal you will be having. Find the dual, and for this dual again find the dual, and that will be primal. This is the proof. So just write any example. Here the previous example itself I have written, and z dash we got. Now for this z dash again find the dual. So here it is minimize, so change it as maximize. Z dash it was, and here go for z dash dash. Okay, now see these are the constants, right, on the right hand side. Now this will become the coefficients of the objective function, and this will become the constants on the right hand side. And same way again take the transpose of this matrix. Okay, so here it will be 1, 2 and 1 for this 0, 1, 2 and 0 here, and for the second it was 1, 0 and 1. For the third it is 1, 1 and 3. This is what we are having. Now take the transpose. So it will become 1, 1, 1, 2, 0, 1 and 0, 1, 3. See, 0, 1, 3. Okay, based on that you have to form the new constraints. Very simple. Take the transpose again. Okay, and here it was, the question was x1, first dual it was y1, and this for the second dual it will become z1. See this is the same as the primal. Okay, so this is a proof. That is, this will be this is a commonly asked question in examination. That is, prove the statement dual of a dual is primal itself. Primal you will get, find the dual of it, and again find the dual of the dual. Okay, so here 1 and 3, this is the first equation, this is the second equation, and this is the third equation. Okay, so now first equation and the third equation are same, so it is proved. Okay, here one more question is given to prove the statement dual of a dual is primal itself. Okay, so maximize is given, convert it into minimize, and from there to maximize. So equation 1, that's the original one, and dual of the dual, that is 3. Both are same. Okay, hence it has been proved. These are the steps which are to be followed for the conversion. First, construct dual from primal. We need to convert the problem into canonical form. Change the maximization type of the objective function into minimization. The number of constraints in the primal will be number of variables in the dual, and vice versa. The cost coefficients of the objective function will become the right hand side constants, and vice versa. See, all the variables both in primal and dual should be non-negative. And the transpose of the body matrix, see, transpose you have to take. Okay, if a variable is the primal is unrestricted in sign, then the corresponding constraint in the dual will be an equation and vice versa. That is the equality. You have to change, very simple this is, you have to change the inequality in the question. If it is greater than or equal to, convert it as less than or equal to and vice versa. Okay, so these are the steps which are to be followed for constructing a dual from primal. In today's class, we have learned how to find the dual form of the given LPP. This is very important question, and the proof which I have gone through this, that is also a common question. Hope it was clear for you. Thank you.